Hello and welcome. This is going to be our lecture video for May 6th. Let's go ahead and get started with this problem here. Hopefully you got your notes out. You put today's date at the top. Go ahead and try to draw out this situation. The distance from Lincoln, Nebraska to Jackson, Mississippi is 690 miles. So Lincoln up in Nebraska, we'll put up here. Jackson, Mississippi, we'll put down here. And that distance is 690 miles. All right, Jackson to Atlanta is 350 miles. So Atlanta we'll put over here, and that's 350 miles. And then Atlanta to Lincoln is 833 miles. All right, so here, let me connect these up with my straight lines. We have a non-right triangle. Well, it might be a right triangle, but we're going to assume it's a non-right triangle until proven otherwise. What is the area of this triangle? If we started a new country and we just said it's the triangle made by these three cities, how big of country did we just make? Well, to use our area formula, area equals 1/2 base times height times the sine of the angle in between them. Or we often write this as AB sine C. Well, we need an angle to make this work, and we don't have any angles here. Now, if we wanted to use law of sines to find an angle, you'd already have to have one angle, so that's not going to work. So we have to use law of cosines. The law of cosines is that a squared equals b squared plus c squared minus 2bc cosine capital A. And this works. You can rearrange these letters. You can have it be a b squared over here. If you swap the a's and b's, it works. If you swap the a's and c's, it works. But this will work for us. So this uses 3 side lengths and an angle. If you have 3 of the 4 pieces of information, you can always solve for the last one. So that's what we've got here. So I'm going to solve for, we'll say this angle here, because I've got it set up cosine A, and this is already point A, so that makes sense. All that matters, B and C can swap places, is just that I put this 690 on the other side of the equation. So 690 squared equals 350 squared plus 833 squared minus 2 times 350 times 833 times the cosine of A, and that's our missing piece of information there. All right, let's get the calculator out and combine some of these numbers. So I'm just going to do this out loud. So 690 squared. I'm going to subtract away the 350 squared, and then I'm going to subtract away the 833 squared equals, switch colors, negative 340,289 equals, let me combine all this now, so negative 2 times 350 times 833 equals negative 583,100 cosine A. Divide that over there. I'm not going to write out the whole thing. It's a big number. So negative 3,400, 340,289 divided by second answer. I get this decimal, 0.58 equals cosine A. And we take the inverse cosine of that number that is in your calculator still, hopefully, and you get 54 degrees. So angle A equals 54.29 degrees. Now, technically, the inverse cosine of 0.58 would also be 360 minus that number, because you get an answer in the first and fourth quadrants. So 305 degrees, but obviously this can't be 305 degrees. In fact, that would be the external angle there, which we do not want. We want the internal angle. So we just keep that one measurement. It's what your calculator gives you anyway, so don't worry too much about that. Just wanted to kind of point out that piece of information. All right, now we can plug that in, this angle here in conjecture with its two side lengths to find the area. So we'll do that over here. Area equals 1/2 times 350 times 833 times the sine of 54 degrees. Plug that whole thing in. Let's see, I gotta get the number back. I can just type it in. So sine 54.29683951 times 833 times 350 times 0.5 for the 1/2 gets us 118,376.8, and this was in miles, so this would be miles squared, or square miles. Square miles. So very big area. Draw an arrow. This number came over here. Just can't really see it. Okay. So if you're given three side lengths, use a lot of cosines to find an angle, then you can use your area formula. Goal for today is to add our angle sum difference, half and double angle identities to our repertoire of identities that we can use either when solving or doing verifications. Why are we doing this? To be able to find exact values for a wider variety of angles and to do a wider variety of identity verifications. All right, if you want to copy these down, you can pause it and copy these formulas down. Here's how it looks on the cheat sheet that I posted. They use a kind of an interesting symbol here. So the sine of A plus B equals sine of A cosine B plus cosine A sine B. And then if it's a minus, this becomes a minus. But this symbol here, this means that if the plus or minus becomes a plus, the minus plus will become a minus. It means they take opposite signs. So we can see with our cosine formulas, when it's A plus B, you use a minus here. When it's A minus B, you use a plus here. So they use this symbol a few places to show that you use the opposite operation when you plug in these formulas. Okay, so here's the kind of problem that this can help us solve. What is the exact value of the sine of 105 degrees? So this is not one of our special triangles. We can't use a special triangle to get an exact value here, but we can split that 105 into two angles that we do know, or two angles that do relate to special right triangles. You can split it into a 45 and a 60. All right. I'll say these are two angles on the unit circle. That we know. So the fact that we know these two means that we can use the addition identity to find an exact value for 105, which is one that we don't know. So here's how this is going to look mathematically. Sine of 105 is going to become the sine of 60 plus 45, which then we're going to use this identity here. Sine of A plus B becomes sine of A cosine B plus cosine A sine B. So this becomes sine of 60 cosine 45 plus cosine of 60 sine of 45. And although now we have 4 trig functions instead of 1, these are at least 4 that we know the values of. All right, I'm just going to draw a 45 and a 60 in standard position. So if this is a 45, this would be 1, 1 in the square root of 2. And then we'll do a 60. this is a 60 down here, and that's the 30. This is our 1, 2, and the square root of 3. I can go ahead, I can label this as opposite and adjacent and hypotenuse. All right, sine of 60. So sine of 60, look here, opposite over hypotenuse, square root of 3 over 2. Cosine 45, adjacent over hypotenuse, 1 over the square root of 2. Plus cosine of 60, 1/2. That's a good one to just double check in your calculator. Since it's not irrational, you just do cosine 60, you get 0.5, means that you drew your pictures all right. And then sine of 45 is 1 over square root of 2. All right, now it's just, so that's our answer. Now we just have to simplify it. So square root of 3 over 2 root 2 plus 1 over 2 root 2 equals the square root of 3 plus 1 over 2 root 2. I don't want to square root in my denominator, so I multiply by root 2 over root 2. And I get the square root of 6 plus the square root of 2 all over 2 times 2, which equals the square root of 6 plus the square root of 2 all over 4. All right, so you can get your calculator out and do sine of 105 right now. You get this decimal. Squaring it doesn't make it rational, so it's really hard to figure out what irrational number relates to this decimal. But by doing this math, we got this expression that is the exact form of sine of 105 degrees. So let's plug this into our calculator. Square root of 6 plus the square root of 2. Hit enter, divided by 4, and I get that exact decimal that is the sine of 105. So I think this is really cool because we could kind of use the calculator to cheat on other exact values for trig functions, but here you cannot. Plugging in sine of 105 does not reveal this irrational expression at all. And it's really hard to work backwards from that decimal to this irrational expression. You have to know how to do this. There's no workarounds. All right, exact value of tangent of 15. So I can't split this into some addition because it's smaller than any of our known lengths, but I can split this into 45 minus 30. And those are two angles on our unit circle. So now that I've got tangent of 45 minus 30, I got to go get that tangent. So A minus B is going to become tangent A minus tangent B. So let me do that first part. Tangent 45 minus tangent of 30 over 1, and then here we see that symbol, so this was a minus, so this is going to flip to be a plus. 1 plus tan A tan B. 1 plus tangent 45 tangent 30. All right, let's draw a 45 and a 30. To plug in here, so tangent of 45 opposite over adjacent, this is just 1 minus tangent of 30 opposite over adjacent, 1 over root 3 over 1 plus 1 times 1 over root 3. And now we got to simplify this. A little bit of a pain to simplify these sometimes because you got to get that radical out of the denominator. Here's how I would do this. I would turn this into root 3 over root 3 minus 1 over root 3 all over, I'll do the same at the bottom, root 3 over root 3 plus 1 over root 3. Now I've got root 3 minus 1 over root 3 all over root 3 plus 1 over root 3 multiplied by root 3 over root 3, and these would cancel out. And now I got to multiply by the conjugate, so root 3 minus 1 It's the only way to get rid of a binomial with a square root. Whatever you do to the bottom, you do to the top. Foil these. So now I've got 3 minus root 3 minus root 3 plus 1 over 3 minus root 3 plus root 3 minus 1. These cancel out. This becomes a 4 minus 2 root 3 all over 2. Distribute that division, and we get 2 minus root 3. And then these are pretty easy to double check. Just do tangent of 15 in your calculator, then do 2 minus the square root of 3 in your calculator. Decimals match, so we're good. Okay, double angle identities. Here they all are. They're very difficult to memorize, so just if you're going to use these, I'll provide them on a test, or you can just have them handy. But they can be useful when doing verifications. Here we've got a verification. We've got to verify and state the domain of validity. And the key that we're going to have to use a double angle are all these 2's hanging out. So 2 sine cosine, that looks familiar. That matches this right here. So 2 sine cosine can become the same as sine of 2x. So this right here, by a double angle identity, we'll write a D there, becomes sine of 2x. All right, now we got cosine of 2x equals 1 over tangent of 2x. All right, now cosine over sine equals cotangent. The 2x will just come along for the ride, so this becomes cotangent of 2x by one of our quotient identities. And now by a reciprocal identity, I can do the same thing over here. 1 over tangent of 2x is the same as cotangent of 2x. Two sides match, so we complete our verification. Let's go back through. So I've got sine and cosine. That's opposite over hypotenuse. That's adjacent over hypotenuse. They're both in the denominator. So I've already got both in the denominator. So we're going to have to say x cannot equal, it's, I think, n pi over 2, where n is an element of the integers. Now that I'm thinking about it, the fact that this is a 2x here, this is opposite over adjacent. There are more restrictions here. I actually don't want to go through this. I think it's a little bit too in the weeds, but technically 2x here cannot equal 0 either, which happens when the adjacent is equal to 0. Actually, it might still balance out to be this. I'd have to think about that one. Let's just don't even worry about the domain of validity with double angle ones. Here's another one to verify. All right, 1 minus cosine of 2x over cotangent squared of x equals 2 sine squared tangent squared. All right, this 1 minus cosine of 2x looks familiar. Do we have something that's kind of like that? Is there a way to rearrange? We don't have a squared. Maybe not. Maybe that's not what we're supposed to do. Let me pause and think about this one. Make sure I pick the right identity to start with. Okay, this is the identity we want to start with. It does have the 1 minus cosine of 2x. It's just a little bit hidden. What we need to do is add the 2 sine squared to both sides. Add 2 sine squared and subtract the cosine of 2x from both sides. And now this will be rearranged to be 2 sine squared of x equals 1 minus cosine of 2x. And now that does match there, so I can replace here, using a double angle identity with a 2 sine squared of x over cotangent squared of x equals 2 sine squared x. We could actually finish it right now if we just take that tangent and use a quotient identity or a reciprocal identity to turn it into 1 over cotangent, and then we can move it to the bottom, cotangent squared x. I think we can call that good. Let's not worry about domain and validity again. All right, half angle identities, here they are. You can copy them down. So 2 more problems, we can do this. All right, what's the exact value of 112.5? So this 0.5 gives away that we're going to be using a half angle, because I can express the 112.5 as 225 over 2. So this is still equivalent. I just rewrote the decimal as a fraction. But now that it is something over 2, I can come use this identity right here. So plus or minus the square root of 1 plus cosine of theta over 2. So plus or minus the square root, I already forgot it, 1 plus cosine of 225 over 2. Yes, okay. And yeah, notice just the 225 is theta, because if we look at the setup, it's theta over 2. So now it's the 225 taking the place of theta. And cosine of 225, we know what that is, or at least we can figure it out pretty easily. 225 is this angle down here. Its side lengths are -1, 1, and the square root of 2. So we go adjacent over hypotenuse, we get 1 over root 2. So we've got plus or minus big square root of 1 plus 1 over root 2. Actually, that would be a -1 as well. So that'd be -1 over root 2 all over 2. And now we just want to simplify this. We'll just see how far we can get with the simplification. I can combine these, make this plus or minus the square root of root 2 over root 2 minus 1 over root 2 all over 2 equals plus or minus the square root of root 2 minus 1 over root 2 all over 2, which equals plus or minus the square root, make that a 2 over 1, so we can copy dot flop. So it's now root 2 minus 1 all over 2 root 2. Multiply just inside here by root 2 over root 2. And we get square root of 2 minus root 2 all over, this would become a 4. And now we got to think, can I express the inside there as something squared so that I can cancel it out with this square root outside? Let me pause and think about that for a second. All right, I've thought about it. I think the best we can do is distribute the square root to the top and the bottom and make this 2 minus root 2 all over. The square root of 4 is a 2. But I do not think that that can be broken down any further. So we will leave it like that. And, oh yeah, there's still a plus or minus in front, which is implied by the square root, but it's still useful because sometimes we throw out the negative. Okay, tangent of 22.5. So what could this be rewritten as? This could be rewritten as the tangent of 45 over 2. Now 45 is taking the place of theta in this formula here. Sine theta over 1 plus cosine theta. Sine theta, so sine of 45 over 1 plus cosine of 45. All right, let's draw our 45 triangle. It'd be 1, 1, square root of 2. So this here is going to become opposite of right hypotenuse 1 over root 2 over 1 plus 1 over root 2. And now we just got to simplify this. So turn this into 1 over root 2 over root 2 over root 2 plus 1 over root 2, which equals 1 over root 2 over root 2 plus 1 over root 2. These can cancel out. So now I've got 1 over root 2 plus 1. You got to multiply by the conjugate. So root 2 minus 1, root 2 minus 1. So I got root 2 minus 1 over, this would become a 2. Middle terms would cancel out. Then I get a minus 1. Here, I'll write them anyway. So minus root 2 plus root 2 minus 1. And now we've got root 2 minus 1 all over 1, which is just root 2 minus 1. I want to double check this one. All right, so tangent of 22.5. Square root of 2 minus 1. Yep. And it works out. All right. That is that for this video. I think there's anything else I need to tell you guys about these problems. Just, when you're asked for an exact value, look if you can make this number through either addition, subtraction, or by dividing in half any of our identities, or any of our angles in the unit circle, and it should be possible. All right, call that good. Have a great